Hello, everybody. I think one more lesson should do it for Chapter 7, so let's get started. What you see in front of you is a graph of first ionization energies of the first 20 elements in the periodic table. And I'd like you to take a look at the trends that you see and jot down a couple of things you notice. You should pause the video and write down a few things you notice. You can now see some of the things I noticed looking at this graph, and that is the lows are the alkali metals, highs are noble gases, and the trend is a general increase across a period. Okay? There is a definite relationship between atomic size and first ionization energy. If we think back to the previous, well, actually it wasn't a previous lesson, I think we did this in class, we noticed that atomic size decreases from left to right across the periodic table, and the size increases from top to bottom. What we're seeing is as the size decreases, ionization energy is increasing, and as size increases, ionization energy is decreasing. So those two things are related to each other. And I hope you can feel that that makes sense, because if I have an atom that's fairly large and another atom that's fairly small, the distance between the electrons and the nucleus is much greater. So I have a larger distance, and because of the larger distance, a weaker attraction between the electron and the proton. And so that means it is easier to remove, resulting in a lower ionization energy. Let's take just a few minutes to talk about this word stable. I'm going to caution you not to use that word too much, because until you truly understand what stable means, I think throwing it around is not an effective explanation for a variety of things. So if you think about things that could be stable, such as a stable government, or a stable chair, or a stable tripod, okay? Stable in this case means resistant to change. A stable government is probably not going to be overthrown. A stable tripod is not going to flip over. Okay? So that definition actually works for atoms. If atoms tend not to change, we might call them stable. Now, change in chemistry means react. So atoms that don't react, we could say are stable. And that would pretty much give us the most stable configurations are S2, resembling helium, and S2P6 resembling the rest of the noble gases. So we have some evidence to say that this configuration, or 1s2 in the case of helium, this could be NS2P6 because it could be 2s2P6, 3s2, 3p6, etc. Those are definitely the most stable arrangements. So what that means is a particle with this electron arrangement tends to stay that way. Okay? It happens that half-filled sublevels are also a little bit stable. Not S1, by the way, but things like P3, D5, F7 can sort of be stable. I don't think you're going to bump into a lot of that in this course. The significance is that if a particle can have its electrons arranged like that of a noble gas, that particle is a particularly stable particle. So this is a little bit of a review of ranking particles in order of increasing size. So how about you pause the video and get your periodic table up in front of you and see if you can rank this set of 3 and this set of 3 in terms of increasing size. Pause the video, jot that down in your notebook, and then you can restart. So here's what I've come up of using the periodic table trends for atomic radius. Phosphorus and magnesium are both in the 3rd period, but phosphorus is further to the right, which means it has more effective nuclear charge in the 3rd period, therefore it's smaller than magnesium. And calcium is in the 4th period, which is 1 principal energy larger than magnesium. Something similar is going on with this second set. Carbon and boron are in the 2nd period, but carbon is further to the right with stronger effective nuclear charge, and germanium is all the way up in the 4th period, clearly larger than those other 2. I'd like to take a few minutes here to look at these particular first ionization energy values and notice a glitch in the trend. Now, we tend to focus on the trends and not the exceptions, but this is a particularly significant exception that makes for a little bit of a glitch. As we go across the 2nd period, we would expect the atoms to be getting smaller, and that is consistent with their radii if we were to look that up. And we would also then, because the atoms are getting smaller, expect the ionization energy value to increase. But what we notice here is a little bit of a glitch for oxygen's first ionization energy. We go from 1,000 to 1,400, back to 1,300, and then up and up. So everything seems fine except for oxygen's value. Pause the video and think about that for a minute. What might be causing oxygen's ionization energy to dip just a little bit rather than going up? The explanation for this actually stems from electron pairing. In nitrogen, which has 3 electrons in the 2p, each electron has its own orbital. In oxygen, there is one of these 2p orbitals that has a shared pair. And what that introduces is a tiny bit of repulsion, that wasn't present in nitrogen. And that tiny bit of repulsion between those paired electrons causes the ionization energy to go down just a little. This only exists here for oxygen. When I get to fluorine, I've definitely got more paired electrons in fluorine. However, the atom has gotten small enough that the radius is more significant than that little bit of repulsion between electrons in the orbital. So it's just a tiny glitch for oxygen because of electron pairing. We've written a few electron configurations of ions, I think. If not, we're going to get a little practice with that now. Notice that things with a positive charge have lost electrons. So cations have fewer electrons than the atom would have originally had. Okay, so how about you pause your video and get your periodic table handy and see if you can write electron configurations for the following ions. And it is okay, if they are isoelectronic with a noble gas, to simply write the noble gas. So let's see how your work compares with mine. We're probably in pretty good shape on the Na+1 and the sulfide. Things get a little trickier with the rest because actually all of these, I'll put it in a different color, had an existing 4s2 that was the first pair of electrons to be removed. So zinc would have had 4s2 if it were not an ion. Those are the electrons that are removed. Gallium would have had a 4s2 and a 4p1. Those are both gone. Iron is a tiny bit more complicated, not really. The 4s2 is lost to create the +2 cation, and then in order to make the +3 cation, one more electron is removed from the 3d level. So when you are looking at removing electrons, always remember to remove the valence electrons first. Quick review of metallic character. Metals are good electron losers, so metallic character is an increasing tendency to lose electrons. And this can be based upon, pretty simply, the atomic radius. Okay? Potassium versus calcium. Let's see. Calcium atom is slightly smaller. Therefore, potassium is more metallic and is easier from which to remove an electron. Potassium versus rubidium. Rubidium is larger. It is in, let's see, 5s versus 4s. This is a 5s1, this is a 4s1. So the larger atom is more metallic. And germanium versus lead. Germanium is a 4p2, 4s2, 4p2 in the valence shell. Lead is 6s2, 6p2 in the valence shell, and clearly larger and easier to lose electrons, lower ionization energy, more metallic. This last screen is related to the very end of chapter 7, where the text points out the differences in the way metallic oxides and non-metallic oxides interact with water. Okay, so I've written kind of the formula more or less the same way for each of these. Because metallic oxides here have a very polar bond between the X, or the metal, and the oxygen, it causes that bond to be likely to break when the metallic oxide connects with water molecules to create a new compound. In the case of non-metallic oxides, this bond is less polar, and so the bond is stronger and remains. Let me show you an example of what I mean. In the case of metallic oxides, such as magnesium oxide and sodium oxide, the compound forms and the metal disconnects itself from the OH group that is formed, because the bond between the metal and the O is far weaker than the bond between the H and the O that results. And so metallic oxides, when dissolved in water, create basic compounds. They always tend to make hydroxides, and then the metal cation hangs out on its own. Here are two examples of non-metallic oxides. When these compounds combine with water, the non-metal remains connected to the oxygens, forming an anion, and the compound that results is then an acid and an H+ donor. Don't fuss over this too much. We will revisit this later, okay? But it is nice to know the difference that metallic oxides make bases in solution because of the weakness of the metal-oxygen bond, and non-metallic oxides make acids in solution because of the relative strength of the non-metal oxygen bond.